Today I will talk about innovations in sample prep, sample analysis, and lab management to help with pesticide residue analysis in food. Pesticides are used to protect crops, but they can be harmful to humans and other species, and they are challenging to analyze. The term pesticides includes 11 different classes of compounds, each of them against a specific pest. For example, insecticides kill insects, so pesticides are a very diverse group of compounds, and we need both LC and GC-MS-MS to detect them. As governments monitor more and more pesticides, laboratories have to include more compounds in their analytical methods. Another challenge is the matrix complexity. All these hundreds of compounds must be analyzed in food, which itself is a complex matrix, but there are also many different commodity groups from fruits and vegetables to herbs and spices. And last, all of these pesticides have to be identified and quantified in low concentrations to fulfill legal requirements. We have helped and collaborated with scientists all over the world to overcome challenges in pesticide residue testing. We understand that each step is critical in the success of the analysis. By listening to their needs, we developed complete solutions from sample prep, sample analysis, data analysis, and report out. I'll share some innovations in sample prep, LC and GC separation, mass spec, and informatics. And I'll start with the Captiva EMR with Carbon S, or the Enhanced Matrix Removal Technology for sample prep. Sample prep consists of two parts, sample extraction and then sample cleanup. Almost always, sample extraction involves Ketcher's extraction, which is simply adding salt and acidified acetonitrile to the homogenized sample, mechanical shaking, then centrifuging the crude extract. Cleanup is usually done with dispersive SPE or solid phase extraction. Instead of the DSPE for cleanup, we are using a pass-through filtration. The crude Ketcher's extract is passed through the Captiva EMR cartridges and eluted by gravity. It essentially acts as a filter. The unwanted matrices such as fats, organic acids, and pigments are retained on the cartridge, while the pesticide targets flow through as eluent. The collected eluent is analyzed afterwards for LC-MS-MS and GC-MS-MS analysis. The Captiva EMR cleanup has several sorbent varieties to remove matrix interferences from food. For food from plant origin, we have the Captiva EMR GPF for fresh fruits and vegetables, and the HCF for fresh leafy vegetables. We also have the Captiva EMR GPD for dry spices, tea, and coffee, and the LPD for dry nuts and lightly pigmented spices. For oil and other fatty matrices from animals, we have the Captiva EMR lipid. On the left, we investigated milk samples for matrix removal efficiency with GCMS full scan. The Captiva EMR lipid cleanup in red showed 99% of the matrix removal and significantly outperformed the other three cleanup methods. The Captiva EMR lipid cleanup also removed late eluent interferences shown after 30 minutes retention time, which are significant sources of instrument contamination. Then on the right, pesticide recovery results in milk show that Ketcher's dispersive SPE cleanup in blue caused significant loss of acidic pesticides, while the Captiva EMR lipid cleanup showed acceptable recoveries. We used the Captiva EMR lipid to clean olive oil samples prior to pesticide analysis, and the recovery is shown in the graph for 10 ppb spiking level in 6 replicates. The average analyte recovery was 94% with an RSD of 4.3%. Planar or acidic pesticides could be lost during sample cleanup due to sorbent interaction. We looked at the recovery of these sensitive pesticides in bell pepper using different cleanup methods. The Captiva EMR GPF in blue provided significant improvement to the recovery of these sensitive pesticides compared to the dispersive SPE methods. We tested the Captiva EMR in many other food matrices, so please feel free to reach out if you have questions. Now I want to shift gears and talk about another cool innovation, the hybrid multisampler. The hybrid multisampler can run in two injection modes. The classic flow-through, which is how LC usually runs, and the new feed injection mode. When run in feed injection mode, the sample is infused continuously into the mobile phase stream, so it can essentially automate sandwich injections. This is especially useful at large volume injections and for samples in strong solvents after, for example, catchers. So for example, there are challenges in the early pesticide eluders such as methamidofos. The strong organic solvents that the sample is in after catchers is a challenge because the LC gradient starts with an aqueous phase. This leads to peak breakthrough and poor peak shapes, especially as injection volumes increase. This new hybrid multisampler has that feed injection mode to address that challenge. It mixes the sample and mobile phase directly at injection to improve peak shapes and sensitivity. On the right, we see excellent peak shapes with the feed injection mode on the top, even as we increase the injection volume from 0.5 to 2 microliters from left to right. Not only are the peak shapes better, but if we look at the blue bars in these four graphs, we see that the feed injection has good pesticide recovery in strawberries. It could reach lower limits of quantitation or LOQs. It has great linearity, and it has lower relative standard deviations for the early eluding pesticides. So our next innovation is on detection using our ultra-sensitive mass spec. So customers wanted a single method, even the sample prep, to cover a wide range of pesticides in Europe because there are different pesticide panels per country. We tried optimizing the method in tomato matrix. The method used the Agilent Catchers extraction kit, our Agilent standards, as well as our pesticide databases for both LC-MS-MS and GC-MS-MS. We also use the GC and LC columns as well as the GC, LC, and MS instruments. The result is a complete workflow solution. LC-MS-MS had 764 pesticides and GC-MS-MS method had 341 with an overlap of 84 pesticides that can be analyzed by both techniques, giving a total of 1,021 pesticides. The method was validated using Sante guidelines. Here's an overview of the LC and GC method parameters. For LC, we used a Zorbax C18 column with 2 microliter injection volume and a 0.4 ml per minute flow rate. Positive and negative modes were run simultaneously, meaning we used the positive-negative switching in our LC method to run the method in a single run. For GC, we used our widely known pesticide analyzer setup consisting of 2 identical HP5MS columns and mid-column backflush, and then the injection volume was 1 microliter in solvent vent mode, and we used the high efficiency source for best sensitivity. We checked the data points per peak to ensure reproducible quantitation and confirmation of results. Carfentrazone ethyl elutes in the window where a high number of concurrent MRMs is analyzed, and this peak is also quite narrow with a baseline width. We get 17 data points for this peak for both the quantifier and qualifier transition with the 6495D. With the new iFunnel mode settings on the 6495D LC triple quad, it is now possible to select different iFunnel settings per compound transition. We can choose either the standard, fragile, and large molecule. So this feature further improves the analytical sensitivity for certain compounds of interest. For example, ethylphencarb-sulfone and dimetone S-methyl had better analytical sensitivity using the fragile iFunnel mode, whereas for sulcotrione and carfentrazone ethyl, the standard iFunnel mode gave better results. The combination of both LC and GC techniques allows widest coverage of pesticides and their metabolites occurring in food. Due to the structure of this huge class of compounds, it is impossible to analyze the various pesticides solely by GC or LC. So Agilent offers both platforms, and this gives a clear benefit when, for example, positive results have to be confirmed or higher sensitivity is needed. On the left, the sensitivity for silaflofen using LC-MS detection is bad, and this is where GC-MS can help out, because this compound can be analyzed easily with good sensitivity and validation results. The use of the other technique for confirmatory analysis can be demonstrated for bifenthrin on the right. This compound can be reliably quantified using both techniques with good sensitivity and results. On the left, to help maximize uptime, we developed our systems to have guided maintenance to monitor its own health status, and it will give warnings if you do need to do maintenance. Our automated tuning uses AI to optimize the auto-tune so it's faster and better. In the middle, you can schedule the auto-tune. For example, you can set it at 5 a.m. every morning, so when you come to the lab, the system is ready for analysis. On the right, maintenance of the transfer capillary in the front end of the current models of the LC triple quad mass specs could be done without venting the instrument, which could greatly reduce the maintenance time and maximize the lab's uptime. Robustness is of course key for routine testing. We injected 4 ml of black tea on the 6495D for 16 uninterrupted days. I'm showing the MRM chromatogram every 500 injections with great reproducibility, even if you see black deposits in the inlet due to the complex and dirty matrix. And there's so many cool features of our LC triple and LC QTOF, but I'll highlight two. For example, if the system detects carryover, it automatically inserts extra blanks so that the previous sample does not affect the next sample. And the other thing is that if the system detects the sample is outside the calibration curve, it automatically re-injects the sample with less volume. We added the ability to process samples quickly to the LC QTOF as well. If a target pesticide is detected with a short method, it automatically runs the analytical method. But if the target is not detected, the system skips to the next sample without running the longer method, thereby saving time. Next, I want to talk about hydrogen as alternative carrier gas for GC-MS analysis of pesticides. There is no doubt that helium is the preferred carrier gas for GC-MS and GC-MS analysis. However, ongoing shortages and increased prices for helium cause unpredictability. As a result, we start looking for alternative carrier gases, and hydrogen is often considered to be the best alternative. Hydrogen has been successfully used for GC applications for decades. It can provide better chromatographic resolution at higher linear velocity or a faster analysis time. However, there's an instrument configuration and the analytical method needs to be addressed and adapted for hydrogen. It is a bit more complex than flipping a switch. So essentially, we need to ensure that there is a reliable source of high-grade hydrogen. There are optimized GC injection conditions, and there are appropriate GC column configuration, and most importantly, select the proper EI source. This last one, the potential undesirable reaction in the EI source for some compounds slowed the adaptation of hydrogen. Fortunately, Agilent has two EI source configurations that minimize the undesirable in-source reactions, making hydrogen a viable carrier gas alternative for GCMS. So in this section, we will address how to keep the retention times with hydrogen the same as with helium, how chromatographic resolution and peak shape looks for pesticides with hydrogen, and we'll also address the unique ability of the hydrogen-optimized EI sources to preserve the EI mass spectrum so that it's identical with helium and hydrogen, which allows for using the same MRM transitions, same libraries with hydrogen as with helium. And the last one, we will assess the method sensitivity. So let's get to the recommendations for making pesticide analysis with hydrogen successful. So first, let's look at the heart of the GCMS analysis. It's the GC column. So the recommended configuration with hydrogen includes two 20-meter 0.18 columns in a mid-column backflushing configuration. Alternatively, one 40-meter column could be used instead. Please note that the standard 30.25.25 configuration or two 15-meter columns cannot and should not be used with hydrogen because of the insufficient GC inlet head pressure. The advantage of this configuration is that it allows for maintaining the same retention times with hydrogen as those observed with helium using the conventional 30-meter column configuration. Here, we see that the chromatograms acquired with helium on the top and hydrogen at the bottom for 203 pesticides look nearly identical with the same elution order and retention times. Please note that the conventional configuration with two 15-meter column was used with helium and two mini-bore 20-meter columns were used with hydrogen. If we look closer, we will see that a better chromatographic resolution can be achieved with hydrogen. We have two groups of pesticides, pyrethroids eluting here. They are cyfluthrins 1, 2, 3, 4 on the top, and then on the left, and then cypermethrins 1 through 4. When we are using hydrogen carrier gas with a corresponding column configuration, as shown on the bottom, we can get better chromatographic resolution while maintaining the same retention times and elution order for these isomers. Maintaining the same retention times with hydrogen as with helium is clear. You have to invest time into changing columns, but you don't have to waste any time on remeasuring the retention times. Now let's talk about GC injection conditions. We strongly encourage you to use the multi-mode inlet, which enables temperature programming and other injection modes for pesticide analysis. generally, and for pesticide analysis with hydrogen carrier gas specifically. Using the MMI, we can implement the solvent vent injection mode, which we find is the best for the analysis of pesticide with hydrogen. The 2mm dimpled liner turned out to give the best sensitivity for pesticide analysis using hydrogen. This liner does not have glass wool, hence we have even less of potential active site. Alternative liners that can be considered include either the mid-frit or the bottom frit. We also suggest to increase the injection volume to 2 microliter volume injection. In some cases, staying at 1 microliter or even below that might be sufficient. In some cases where extra sensitivity is required, you may consider increasing that injection volume. And last is that the use of the analyte protectants to increase sensitivity and maintain robustness and ruggedness with hydrogen carrier gas. We use the following recipe from the 2005 paper by Mastovska, Lehote, and Anastasiades, which includes 3 components: diluted in the mixture of acetonitrile with acetic acid, and their work was done with helium, but the effect of the analyte protectants becomes even more prominent with hydrogen carrier gas. We have 2 triple quad series, the 7000 and the 7010, and we have 3 EI sources. On the left, the conventional extractor and the hydroinert sources in the middle are available in the 7000 GC triple quad series. The conventional or standard EI extractor source on the left, also known as inert plus source, is a robust and reliable source frequently used for pesticide analysis with helium. The hydroinert source in the middle is available in the 7000 series for pesticide analysis with hydrogen as carrier gas only. It has the same geometry as the conventional EI extractor source. What's different is the level of its inertness. Hydroinert source provides the highest inertness, and as a result, it almost completely prevents the undesired reactions that may occur in the source when hydrogen is used as carrier gas. This is due to the proprietary inert material of the source. The last source, the high-efficiency source, is exclusively available in the 7010 GC triple quad series. It can be used for both helium and hydrogen as long as the GC conditions are followed for either helium or hydrogen. After an exhaustive study, we found that for the majority of compounds that do not interact with hydrogen, and there's quite a few of those, the sensitivity in terms of signal to noise and minimum detection limits decreases 2 to 5 times when we convert from helium to hydrogen. And this is natural and expected because the hydrogen carrier gas leads to increased noise or sometimes decreased absolute signal of the compound. And to understand which compounds undergo reactions with hydrogen and which ones do not, the simplest way is to look at their mass spectra. So let's do that. On the left, we are looking at the mass spectrum of chlorpyrifos methyl, our retention time locking compound. This is also frequently used as recovery standard in the pesticide laboratories, so it's a pretty good benchmarking compound. The top is the acquired spectrum with helium as carrier gas. That is the deconvoluted spectrum. And on the bottom is the library spectrum. And in this case, these two spectra are perfectly matching, as you can see from the high library match score of 97. This is with helium, and this is expected because the library spectrum was acquired with helium as well. On the right, we are looking at the deconvoluted spectrum of chlorpyrifos methyl acquired with hydrogen carrier gas, and generally the acquired spectrum looks similar to the library spectrum. The ion ratios are predominantly predominantly the same, and the library match score is relatively high at 74. So chlorpyrifos methyl can be qualified as a compound that does not react with hydrogen, and we did not expect any chemical reactions here, but it was great to confirm. Now what happens to sensitivity? Our working hypothesis is that it is going to decrease 2 to 5 times. As we look at chlorpyrifos methyl, at 5 ppb concentration in vial and in commodity, we see that with helium and the conventional extractor source, we have really good signal-to-noise ratio. As we underwent the conversion to hydrogen and we used the conventional extractor source, we observed some decrease in signal-to-noise ratio, and the absolute signal decreased slightly. But we have perfectly detectable signal at 5 ppb concentration. The active maximum residue limit is established at 10 ppb, so sensitivity at 5 ppb is fully sufficient. With a high efficiency source, we saw a very similar pattern. We are able to detect chlorpyrifos methyl with both helium and hydrogen. The concentration was lower with the HES at 0.5 ppb because it is a more sensitive source. As at the concentration 10 times lower at 0.5 ppb, we got about the same signal-to-noise ratio. There was a slight decrease in sensitivity as we transition from helium to hydrogen. However, chlorpyrifos methyl does not present a challenge for the analysis with hydrogen carrier gas, and the conventional configuration can be used. So, for the compounds that do not interact with hydrogen, sensitivity could be drastically reduced with the hydrogen carrier gas if you are using the conventional EI source. Technazine is one example. When looking at the spectrum acquired with helium carrier gas on the left and the spectrum acquired with hydrogen carrier gas on the right, we see that they are drastically different. The 261 molecular ion is almost completely eliminated when we use hydrogen carrier gas. Instead, 231 becomes the base peak in the mass spectrum. The nitro group in technazine becomes reduced to aniline in the presence of hydrogen, hence the 231 base peak ion. So we have a different mass spectrum now, and a poor library match score, and inability to confirm the identity of the compound based on the spectrum. We also sacrifice the sensitivity of the analysis as shown here. On the left, we are able to detect technazine at 0.5 ppb with helium carrier gas using the standard extractor source. On the right, the same standard extractor source used with hydrogen carrier gas, but we are not able to detect technazine at the same level. Not only that, we could not detect technazine at all at the levels up to 50 ppb in the commodity. The reason for that is because the precursor ion 215, 261, and 259 is almost completely destroyed as a result of the reaction in the source. Hence, sensitivity suffered. It suffered to the point that we could not detect technazine at the MRL level of 10 ppb, and this becomes a problem because we definitely need the sensitivity to meet the established MRLs. So, what's the solution? The solution is to use the hydro-inert source that was specifically designed for the use of the hydrogen carrier gas while keeping the same configuration at the extractor source. Its added inertness enables preventing the undesirable chemical reactions in the source and observing the same mass spectrum with hydrogen as we did with helium. The spectrum is exactly the same as in the library if you use the hydro-inert source. The library match score is 94, unlike in the extractor source, which was 59. And sensitivity is sufficient to measure technazine at 0.5 ppb. Problem solved. So if you're using hydrogen carrier gas, switch to the hydroinert source and recover the sensitivity that was lost as a result of the undesirable in-source reactions. But how about the HES source? This is a natural question because many of you might be users of the 7010 GC triple quad or might be interested in it because of its ultimate sensitivity. Here's the answer. The high efficiency source also prevents the undesirable chemical reactions in the source between hydrogen and the active compounds, as evidenced by maintaining the same spectrum with hydrogen as observed with helium, with a library match score of 93, and sensitivity is truly superior any source configuration that we tried with hydrogen. Only with HES source could we detect technazine down to 0.1 ppb in the vial and in the spinach commodity. So the HES source provides the ultimate sensitivity. The hydroinert source provides sensitivity that is sufficient to meet the established MRLs. The difference between the two is the loading limit. With the hydroinert source, the highest calibration point or the loading capacity is higher, so we can calibrate up to 10 ppm for compounds. With a high efficiency source, we enable higher sensitivity, but the loading capacity is lower. So typical calibration curve is up to 500 ppb to 1 ppm. Technazine is not the only pesticide that undergoes the undesirable chemical reaction. These 15 compounds are some examples that we observed out of the 203 pesticides that to undergo chemical reactions, and as a result suffer sensitivity losses in source if we're using a conventional EI source. The in-source reactions were evidenced by lower library match scores. With the use of hydroinert and HES source, we are able to get higher library match scores compared to the standard extractor source because the undesired hydrogen reactions in the source are prevented. The overall calibration performance for the 203 pesticides revealed that over 92% of compounds are successfully quantitated at or below 10 ppb, which is the action MRL limit. So in summary, we are happy to help you with your multi-residue pesticide analysis, from sample prep to sample analysis to data analysis to report out. I talked about the EMR Captiva cartridges to remove unwanted food matrices, the hybrid multisampler to improve peak shape and method performance of early eluting pesticides, our mass spec solutions, our EI sources for hydrogen carrier gas called the hydroinert and the HES sources, and the SLIM system for lab management.